Hi, and welcome back to the second day of the Canadian Underground Forum, the inaugural CUF. So we're going to jump back into another leg of the stool in the new underground, or the new underground frontier, which in the technology side, we're going to be hearing now from Simon Pedley, who's the detection sales manager. I've heard the term detection ambassador with Hexagon and the companies under that umbrella like GeoSystems, etc. So Simon, looking forward to your presentation. Take it away, sir.
Yeah, thank you, Gavin. Can you see my screen as it shared itself?
Yes, looks great. We can hear you well.
Wonderful. Glad to hear it. So my name is Simon Pedley. I'm the detection sales manager for North America and Canada. As you can probably guess by the accent, I don't originate from the US, and especially don't sound like I'm from Atlanta anyway. Started my life 18 years ago working for Leica over in the UK, and through my time, it has all been dedicated to the underground world, supporting people, providing technical support, field support, wherever necessary. Over here in the US, we're building a detection business for Leica and just helping people and understanding what's under the ground and how to mitigate risks associated to the wonderful world of utilities. So for anyone that hasn't heard of Leica Geosystems, who are we? Well, we're a global measurement company, effectively. If you have a geospatial need, then we'll probably make some equipment that you'll probably need. It's quite an exciting year for us here at Leica. We have currently been in business for coming on for 200 years. So this is our 200th year in business. And during those times, we've been pretty much known as a leader in the measurement and information technologies, making complete solutions for anyone across the planet who needs some geospatial measurement completed. But what I'm going to talk about is some different technologies that are going to aid and assist in the world of capturing information about where utilities are. As you would guess from my job title, I'm going to start with ground penetrating radar. That's not where it's going to be limited. We're also going to look at some different sensors that allow us to capture utility information prior to being buried, and also how we can capture information from utilities, but keeping people safer. So we're going to start off with the DSX, and this is a new take, should we say, on the visualization for ground penetrating radar. So it's still ground penetrating radar. We haven't broken any laws in physics. We've still got the same limitations that we've always had. And just remember that GPR isn't an all-seeing eye. It's just one of the tools in the toolbox that allows us to understand what is going on under the ground in that world we can't see. So the reason for the tool even to be in existence is that a lot of the times, and anyone else that's really used radar over the years is used to seeing a radargram, that gray mesh that's on the left-hand side of the screen. Now, this can be a challenge. If you're a utility professional, working with that is no issues. You can glean a lot of information from it. But this piece of technology is geared around damage prevention. You know, we're not trying to sell this to a utility professional. We're just trying to mitigate as many utility strikes as we can. How do we make the technology simpler so people can understand what's happening under the ground? So we looked at it and we see what's on the left, the radargram, as a challenge. It's a barrier for people to feel comfortable and interact with and get the best information possible. So what we did with the DSX is we changed the workflow. We changed the approach of how we look and how we find utilities, and looked at it from a best practices point, where we should cover an area in multitude of directions with a multitude of tools. And what we get, instead of looking at the radargram, we gave a tomographical image, which is what we can see on the right. It almost looks like, you know, a thermal imaging view of the ground. And we're just looking for anything long and linear. And we're going to use algorithms to help determine where these cables and pipes are, should we say. So, as I said, it's ground penetrating radar. We haven't changed anything here. The antenna, to be technical, is a 600 megahertz antenna. You're going to get around 6.5 feet of penetration. About 2 meters is where it maxes out on its algorithms and processing this information. As you would expect, it does link with positioning sensors, total stations, or GNSS. This doesn't matter if it's a Leica or if it's a competitive unit, we communicate with all. But really the change, the thing that we did different is with the D-Explore field software. And now this is where, well, really the important part there is the word field. We don't need to process any data back in an office. Everything we see is delivered within minutes within the field. So we acquire the information, we produce the visualization, it assists in the interpretation, and then we can document everything in the field. And when I say document, that can be a DXF, DWG, Esri shapefiles, PDF reports, everything's done, directly in the field, and we can work on this information almost immediately. So to get this, what did we do? So like all ground penetrating radar, we need to cover an area in 2 directions. We call it the grid scan. So we need to cover an area, and the biggest grid scan we can do at any one time with the limitations on the speed for the processing is 33 feet by 33 feet. Okay, so 10 meters by 10 meters. We collect over the area in 2 directions, and we're going to have a scanning interval of 18 inches or half a meter, and we're going to cover the area. So the only thing that we see at the start of any project is making sure we get the best data into the system as possible. The better the data we have in, the better the information and the data we get out from. So we collect the data. We can then analyze that data. So we collect everything, we hit a button that says analyze, and within about 30 seconds, we get this process model of information that looks like a thermal imaging view of the ground, should we say, the tomographical image. We have a depth slider on the right-hand side, so we can go through in 5, 10 centimeter chunks and look for anything that's long and linear, typically what utilities are. So as we go through these different depth layers, we can start to see these linear objects, and this is where we can utilize the algorithms that are within the system. So when we can see something, we hit a button that says add utility, we slide our finger down what we believe to be a pipe, that anomaly, and the system is going to make the determinations for us. So it utilizes algorithms to go and look at the radiograms, effectively, that bit we don't see. And can it see a hyperbola? Can it see these indications of utility? If it can, it agrees, marks it, and then utilizing a semi-automatic pipe tracking algorithm, it'll draw the utility line in for us within a matter of seconds. So as you can see, we have the first line marked. Now, like I said, it can guide us. We don't have to be brilliantly accurate, and it puts it in the exact location it was detected. So for example, I drew the line as a wave, but the software has the ability to put it in the correct location for where those utilities are located. So as an example, we're going to work through this block of data. We're going to go all the way through it, identify the utilities that we can see in that area, and then we're all good. So the next step would be to turn that data view off. We no longer need it. We've identified where the utilities are. The next step is to understand where these are. Do we need to mark the ground or whatever? So we can turn that layer off, and then we have the utility pipes. So we can understand where things are going, how they're running, so on and so forth. So if we were utilizing a positioning sensor, we hit lead to utility, and we're able to mark out all those utilities. We get the XY direction, and it tells us how far to walk, where to mark, and so on. So it's extremely easy. If we hadn't used a positioning device, so we didn't have a total station with a GPS antenna connected, then we can use an arbitrary grid, just lay that on the floor, and we can just pull tapes to measure where those utilities are located in that work area. But not only can we see them in a 2D view, we know with radar that we can get depth estimation. It is an estimation. We don't know exactly how accurate it is, due to a number of factors, but we can get that additional information of how deep utilities are. So I can hit a button that allows me to rotate this as a model. So I can rotate that model of data and understand how deep those utilities are, how they interact with each other. That can change a dig plan, a dig process. But we have that little bit more of information, and it also looks more visual and easy to understand when we're directly in the field looking at the ground that we just scanned. Now, for documentation wise, during the collection or at any point, we can add other bits of information referred to as a point of interest. So like I said at the beginning, GPR is GPR. It's not going to allow us to find everything, and you're probably going to use a locator before you use a GPR. So if you find something with a locator that you don't find with a GPR, you know, we can put the marks in and say, yep, we found something here, and we can code it as an electromagnetic locator location point. Or we might have called a water line, and we know that because it's connected to a fire hydrant, or we can see a valve in the ground, or many other different things. So we can start building some extra layers into this picture. But anything that we see here during our export does go out. So anything you put in here, size-wise, drawn-wise, will be exported during the DXF process, or as a PDF. Every piece of information is captured. So within a matter of minutes, and I do mean minutes, we're able to get a complete understanding of what's in that little area under the ground, where the utility is going, what are the dangers, how deep are they, so on and so forth. But like I said, it's there for that prevention. Someone's going to be digging and they want to do a redundancy check on that area just to make sure that all utilities have been marked correctly, they are accurate. You know, it's just that thing to give a little bit of self-confidence. So if we move on to a different technology, and again, it's not its normal home, should we say, and we have a product called the BLK to go. And as you can see from the image on the screen, it was pretty much invented for architects to capture information from inside buildings so they can design refits. But it's not its limitation. We can do other things with this technology. So what is this tool? Well, the BLK to go is a handheld image laser scanner, and it basically recreates spaces in 3D as we move. So it does everything instantaneously. We don't need to worry about it. We just walk with the system. It captures images that are dimensionally accurate, and it produces a point cloud in real time. It does it by using SLAM technology as we go through this space. So if we reference this to what utilities are, there's a video here, but effectively, you know, we're putting utilities in the ground all the time, and we don't necessarily capture all the information about them. So I've got an example here of a subdivision being built, and before we bury all the pipes, we're going to walk around with the system. So here's a system in use. As we walk over the area, we're going to capture the information. We're utilizing the Grand Slam technology, which is an IMU and virtual inertia system as well. And to view the data that we have, it's just a very simple process of plugging it into our laptop. And like I said, we've already created that point cloud. So we can get a full understanding of where those pipes are in the ground. And we can also model those pipes for documenting reasons. So we can walk around the site, capture this information, and understand where these utilities are. We've got the accurate information. Everything can be measured to its direct. It's a measurable and accurate point cloud of where the utilities are, sizes, diameters. You know, was a tracer line installed? We can see all this information by utilizing this technology. Very quick, very easy to use. We can just walk around and collect all this data and know with confidence that we have it. So if you're not 100% sure how this SLAM technology works, what is it? What does it do? So let's just look here. So we utilize something called Grand Slam in this technology. So SLAM technology is simultaneous localization and mapping, but we also combine it with high-speed dual-axis LiDAR and a camera system and an internal measurement unit. So it always knows where we're going, and because of all those bits of technology within it, it makes it self-orientating. So it knows when we walk upstairs, it knows when we turn left, we turn right. It knows exactly where we've been, how we've walked, every single piece of information that we could possibly want. Because we're walking with it, and because of this Grand Slam technology, it makes it extremely fast to capture this data wherever we're going. And we're not just limited, you know, by walking around. We need to make sure, because it can capture the trajectory that we were taking, we can also capture under things. So we're not just limited to where we walk holding it. We can take the system however we want, point it in the air, take it down under things, take it into holes. We can do whatever we want. It really is unbound because of the lightness of that system. No need for tripods, no need to set up. We just turn it on and we walk with the system. Nice, simple, easy, and very fast to capture this data that we want. Okay, so like I said, just to recap, the BLK automatically builds the 3D point cloud while in motion. Okay, so we don't need to do any processing, it's all automatically done for us. So from the moment we begin the scan session to the moment we turn it off, all that imagery and 3D data are combined together. So it's immediate picture and understanding of what's going on. So that's one of the solutions, you know, that we can have if we've got open trenches and capturing the information before it goes in. But then we also have another need for capturing information for the utilities. And as we can see here, we have a GPS antenna with some little hole cut on the side of it. So this is our imaging antenna. So the GS18I, as we call it, is the predecessor, well, is the next level on from the GS18T. So as you would expect, we've done something else to it. We've innovated it. We've tried to push the boundaries further in getting GPS measurements in difficult areas by utilizing visual positioning technology. So effectively, it's got a camera inside it, and that camera is running on like any drone system does on photogrammetry. So that's built into the side of this GPS antenna. So any picture that we take, we can take a measurement within it, and we can get survey grade information, or survey grade point, should we say, from that antenna. So how does this help us, and how has this changed things, and what does that mean? You know, if you're not 100% familiar with GPS, what does that mean? So we've got an image here of a building. It doesn't matter what it is, but we've got a picture of a building here, and we've got trees surrounding it. And if we were utilizing a normal GPS antenna, we're going to have some issues getting underneath the trees too close to the building, because that antenna needs to have path to the air. It needs to be able to get to the signal, you know, to be able to take that shot. When we released the GS18T, we managed to push those boundaries further. Because this can tilt, we can tilt the base of the pole into those difficult to reach areas, but we can't get all the way in, okay, but we can get closer. But by having the imaging technology within the GS18, nothing is now a limitation. You can see the whole building is green. We can take a shot from the ground, up in the air, under trees, under canopies, anywhere that's necessary. We can take these positional pieces of information from. So what does this actually look like? So it's not what we see on the screen, but as we utilize in the system, all those green dots, all those green points are every single measurement that we can take in real time. We can see all these different points. And as you can imagine, to try and take those shots as a surveyor in the field, you know, it's going to be one, difficult, hard to get to, and it's going to be time consuming. But really, it's just a click of a pen on the screen, and we can take any measurement at any point that we want. When I'm talking about surveys, so how am I going to get this into the world of utilities? Well, we know we've got some issues, and, you know, like I did with the BLK to go, we know we have open trenches. Okay, so there's no reason why I know where I start and I know where I'm going to finish. I can just literally point the antenna head into a hole and capture all the details of what's in that hole. Whatever the utility is, I can get full information of what's down there, understand where these utilities are, take measurements to them, do whatever I want, because of the IMU and the camera built into that antenna keeps me accurately positioned. So that's one great feature of it. Another great feature is that we have an image of whatever we take. We can effectively do the QA/QC in the field and understand what's happened. So we have an instance, let's say, where we have a utility professional going out and marking the utilities, you know, as we can see here. And the surveyor goes out and he's trying to survey these marks after him. He might look at this area and think, not 100% certain what this means. Is this a T? Is it a bend? Is there two lines together? I'm not 100% following. But my expertise, I think it's this. But we have a picture. We have an understanding of what was laid on the ground, and we can make that change if we needed to in the office effectively immediately. You know, we don't need to send someone back out to relocate it. We don't need to send someone back out to resurvey it, because we have a picture of what was initially laid in the first time, and we can make those changes, those adjustments to that document. And we can also know that those positions or those measurements that we take are accurate as well. They are to survey grade accuracy, which is quite powerful. But we can take it a step further as well. You know, we've all seen surveyors trying to take shots onto certain things in the right of way. If we have manhole covers, we have valves that need to be captured. Typically, a surveyor has to go into the roadway to take those shots. He has to be in danger. So now, again, we have an image of the area. We can take those shots, those measurements, those points from relatively safety. We can be on the sidewalk, walking down, saying, yeah, we need to capture this area. We've got a picture, number of little images. Let's take those shots from a safe distance and carry on. And again, it works if someone's been into that right away. They have done their utility locate. They've laid the paint on the ground. We don't need to put a second person in harm's way. We can reduce the amount of time we have people in danger. If we've got an image of it, that we can take accurate measurements, we can produce utility maps and survey maps significantly faster by keeping everyone, you know, as much as we can away from danger. But again, the important part is not only taking that measurement from the image, but we have it there from a QA QC. We can understand what determination was made, what the site looked like at that time. We just have more information about what went on. So if anyone has any questions, I believe I have 10 minutes left. So feel free.
Yeah, sure thing, Rob. It seems like people want to drill into some details. So,
hey, Gavin, it looks like you're talking, but I can't hear you. Let me see if it's okay. An error on my end.
Can you hear me now, Rob?
It was on my end. My computer muted its audio. I do apologize.
Oh, okay. Well, there's a lot of people that said that they don't want to hear any more from me anyhow. So, yeah, some people want to drill into some tech details. I guess people are getting their GeoGeek on, me too, me included, and I have a few questions. So I'll give you a heads up. I have a Stream C.
Yep.
And yeah, I mean, there was few changes in GPR for so long, as you pointed out, and then while the array type did change things quite a bit, made that tomographic sort of representation possible. But past 4 years has been just constant software development. Mm-hmm. And yeah, it's great to see a lot of that maturing. Yeah, there's still a little bit of tea leaf reading, you know, but that's dependent on lots of things, you know, the conditions and soil types. And
we can't change physics.
Yeah. Okay, so question about the BLK2Go, the SLAM. Somebody's talking about getting that to register to like a project or a, you know, jurisdiction datum, because, you know, it's collecting relative to itself that point cloud through the, you know, visual SLAM type Grand SLAM. But do you drop targets on the ground so you can, you know, register it to the datum?
Yes, that's what you would do if you needed to register it to the datum. You don't have to if you just, like I said at the beginning, it was really for architects to capture the current real life inside. But yeah, you can reference it like you would any normal scanner. It is a scanner at the end of the day.
Okay, great. Yeah, you got a trench open, somebody walks it quick, you've got that captured. Oh, does it take photos as well?
Yes.
Okay.
Photo on LiDAR. Yeah.
So you've got the cloud and the photos as well. Okay, question, what is the depth of capture that the GPR can capture? Well, you'd mentioned 6.5 feet, but if you want to talk about the depth and what might affect how deep it could go.
Yeah, so we actually start processing the data at 7 feet, so almost, you know, just over 2 meters. So we actually put a hard cut in our data to say we're not going to process any deeper, but we don't know actually even if we're seeing that depth in any way, shape, or form initially. The problem with GPR is we don't know what the ground condition is. You know, ideal world, for example, you know, I don't live far from Florida. If I was pushing my GPR into Florida, they have nice sandy conditions, the sand isn't dense and the signals can travel easily. But I actually live in North Georgia and, you know, not far from the start of the Appalachian Trail, where we have a lot of dense, heavy, wet clay. So up here, doesn't matter what system I run, I see about 4 feet because of the density of the clay. And, you know, Georgia's known as Hot Atlanta, but we also do have a lot of rain. You know, we have rain, you know, within every 10 days, and the ground is typically always saturated. So we can't see that deep. So the ground condition has the biggest effect on ground penetrating radar. So in an ideal world, it can see 6.5 feet, but it really does come down to the ground condition of exactly how deep we can see. And again, that's why we refer to it as a tool in the toolbox. It's not going to find everything in that 6.5 feet block. So it's usually just one of the tools there to help us effectively see what's under the ground.
Yeah, certainly. Yeah, we've got a mix of glacial till, and you know, Seattle's known for rain at certain times of the year. Although we want people to think it rains every day, so less people move here. But it's the glacial till. There's areas of clay. There's a few areas of sand, but it's the moisture also. But even when it's in the worst condition, what is a benefit, talking to other users as well, is at least you know there's something there. You may not get the nice 3D view out of it for in all conditions, but at least you know, you verify that there is something there quickly. Okay, question about the is the GS18I.
Yep.
Yeah, I test drove that and walked a trench with it, so I can testify that the precisions it claimed shocked the living daylights out of me. They were actually pretty darn good. So what's the workflow to get that information into, say, an asset management system? I guess that would depend a lot.
Yeah, it does depend a lot on what that asset management system is. So it's typically a normal survey tool. To utilize the imaging part of that antenna, you would have to be using our survey software, which is called Captivate. So you're going to have to do some transformation from whatever we produce it into whatever you need it in. If it's going into an asset mapping database, you know, if it's an Esri one, then we're going to have to do some other conversions to it. So yeah, it's got a lot of open-ended questions on that one of exactly what that workflow would look like, as it would depend on, you know, what one we have, and two, what do we need to go into.
Okay, and also, you know, this from my experience is that you don't necessarily have to resolve all those points in the field. It could be that you just send someone out to capture it, and they could take it back in. I think it's called Infinity software.
Yeah, it's
you
the
can
same.
actually pick out those points later.
Yeah.
And then it looked like there were, yeah, a number of export options. Well, it's point data, so point data and images. So, you know, simple ASCII file could even get down to that level.
Yeah, you're correct. Yeah, we do run it into Infinity, and that's just our processing software for pretty much every single one of our antennas. So yeah, everything goes and resides in our Infinity software, and then multitude of different outputs.
Yeah, before we wrap it up, a general question: are you seeing an acceleration of this data collection? I mean, I'm seeing a lot more effort being put into utility asset management lately, underground utility asset management. Is this what you're seeing around the world?
We are. Well, yeah, it's a little bit different this past year. Things have changed slightly with the wonderful joys of COVID, but we have actually seen an acceleration during COVID in a way of capturing this asset data. And the reason why we see the acceleration is because it was the joy of COVID almost for us, is that there was a heck of a lot of less people driving on the roads. So everywhere was a little bit safer for us to work in. So we did see dramatically over the globe an uptake in mapping of utilities because it was safer to do it. You know, road closures were easier and were less of a problem if we needed to close down lanes, so on and so forth.
Oh, okay. I didn't think about that aspect. That's pretty cool.
Yeah.
So Simon, thank you again for the presentation. It was great to see multiple technologies. You know, I guess people's in their mind, they just think GPR is the thing for underground, but it's great to see these other options, actually, which we've seen over the last 2 days. So we're going to wrap it up for now and go into a break. We want to see everybody back at 25 past the hour for the next presentation. So thanks again, Simon.
You're more than welcome. Thank you for the opportunity, and have a good day and weekend.
We'll see you at InterGeo.